Peter, you can see my screen, is that right?
Yes, I can.
Yep, okay. So hello everyone, I'm Dave Wilhelm, president of GSM, the Geological Society of Minnesota. Welcome to the second to last GSM lecture for 2020. Thanks for being part of a tradition that goes back 82 years to 1938. This lecture's topic is Mesozoic Vertebrates of Antarctica by Professor Peter Makovicky of the Earth and Environmental Sciences Department at the U of M. This is going to be our second virtual visit to Antarctica this fall, and I'll introduce Peter shortly. As most of you know, the format is we're going to have a few announcements, and then Peter's 1 hour lecture, and then we'll have Q&A. All participants other than the host, the presenter, and the moderators are muted. For most lectures, including this one, Randy Strobel is the host. He and I are the moderators. As always, Randy, thanks for setting up these Zoom webinars. The Zoom platform offers a number of means for interaction that we will use. We would like to handle most questions at the end. To enter a question at any time during the lecture, click the Q&A icon and type in your question. Need not wait until the end. We're going to wait until the end to actually pose the questions, but feel free to type them in at any time. And for those few persons that are joining by phone, we will unmute them at the end in case they have any questions. We might also unmute other questioners if we need to get clarification on their question. If you have a quick question for which you'd like an immediate answer, click the raise hand icon and enter the question. And we'll use our best judgment of whether we want to interrupt Peter during his presentation. Otherwise, and also use raise hand to report any technical issues. And there's also a chat option, and I'll talk about 3 ways we use that in a little bit. Most of the GSM webinars, including this one, are recorded and made available online. We'll send out to members and the other participants and to Peter an email with the link when each recording becomes available, usually in a day or 2. The full lecture schedule is on our website, gsmn.org. As always, thanks to Steve Erickson for arranging another outstanding slate of topics and presenters. The next lecture in 2 weeks on December 14th will be on the glacial history of Iowa by Philip Kerr of the Iowa Geological Survey. So we won't travel quite so far south the next time. This webinar, as all GSM webinars, is copyrighted by the author. We kindly ask that you respect the copyright by not forwarding the Zoom link and not recording the lecture yourself. Thank you. As with our live lectures, this lecture is free and open to the public, not just GSM members. If you are not a GSM member, please open the chat box and type non-member in your city and state or province or country. Also mention how you found out about us. That way we get to see how many non-members attend, so we see how well our information reaches the general public. I think about 5 or 6 non-members registered this evening, so I expect to get a couple messages like that. Of course, we would love for you to consider joining our organization. The membership information and forms are on the website. No requirement to do so, but we're always happy to get new members. Also, we can count the number of devices that tune in, but the number of people watching, but not the number of people watching from each. So we can get a better count of how many are participating. If you're watching with at least one other person, type 2 persons or whatever the number is in the chat box, and then I can add those up later. Continuing education credits. These lectures are eligible for 1 hour of CE credits. If that's something you can use the chat to request a form, include your name and email address. And if you don't want everybody to see this information, there's a chat option that allows only the host to see what you type. And then following the meeting, I will fill out a form, sign it, and email it to you. As announced last time at the recent board meeting, The board decided that our lectures will remain online for at least through April of 2021. That probably doesn't surprise any of you. Normally, the last lecture in May would be our spring banquet. We have left undecided whether we will have a spring banquet or just another online lecture. We'll decide that at the February board meeting. And I hope you find the links of the various geological and other scientific resources I send out useful. I get most of these from you, so keep the suggestions coming, especially as the long holiday break will start in 2 weeks and people may be looking for stuff to occupy their time if they can't visit family, for example. If there's any other announcements, use raise hand. I don't see anything. So I think I'm going to go on and introduce Peter. Peter Makovicky is a dinosaur paleontologist and professor in the Department of Earth and Environmental Sciences at the University of Minnesota. Prior to joining, oh, by the way, I missed something here. Are we recording, Randy? If not, you should turn that on.
Yeah, I started recording.
You started, okay, good. I was going to mention it earlier. Anyway, back to the introduction. He's a professor in the Department of Earth and Environmental Sciences at the University of Minnesota. Prior to joining the U of M, he was a curator at the Field Museum in Chicago and served as the chair of its geology department. Peter received his Ph.D. in Earth and Environmental Sciences from Columbia University in New York and his bachelor's and master's degrees from Copenhagen University in Denmark, where he grew up. He has conducted field work in China, Argentina, the US, and of course, Antarctica, and has contributed to the naming of over a dozen new dinosaur species. So welcome, Peter. We look forward to hearing more from you about Antarctica. So I'm going to unshare now, and then you can start sharing.
Okay, thank you so much. And I'm going to share my screen here, and please let me know if it's not actually working. So you should be able to see it now. And it's my pleasure to take everyone on a long distance journey to Antarctica, and not just geographically speaking, but also we're taking a long journey into the past, into the early half of the Mesozoic, or the age of reptiles. So we're going to be talking about the Triassic and the early Jurassic, or the first 150 million years or so of the age of dinosaurs. Now, Antarctica today, as you all know, is a very bleak and ice-covered continent. Its geological history is quite inaccessible. There are only a few places, such as the Central Transantarctic Mountains, where you actually get far enough, or you get rock exposure above the ice caps, and you can actually access that rock history. And if we look at the fauna, the animals that live in Antarctica today, they're extremely charismatic. There are things like Adelie penguins here, this one right off McMurdo Sound, getting all worked up about a Weddell seal that's swimming by. We are all familiar, of course, with these animals from various nature programs. As I said, they're very charismatic. But ultimately, all of these animals are part of marine ecosystems. Even though they may come up on land to have their young, they're tied to the marine food web. And with the exception of very few small arthropods, there are no terrestrial ecosystems in Antarctica today. And for a long time, people didn't know whether that was always the case. And that's, of course, related to the fact that Antarctica is both inaccessible and has an extremely harsh climate. Now, Terra Australis, as it was predicted to be found in ancient maps, wasn't really encountered until about the 1700s, when Western explorers from Europe started sailing around and actually reaching the continent. And the first landfall by people on Antarctica was in the late 1800s by various seal and whaling parties that landed on there. So this really is a continent that has been poorly explored for well under 200 years and really only about a century when we're talking about the interior of it. And so we have very little knowledge of it relative to other parts of the world. And that also holds for its fossil record. Now, obviously, the fossil record was most accessible right here at the tip of the Antarctic Peninsula, close to South America, across the Drake Passage. And this is indeed where the first fossils were recovered in 1904 by a Swedish Antarctic expedition. And as luck would have it, the members of this expedition took with them an American painter, an artist who they wanted to make to paint pictures as well as taking sort of glass photos. And as they landed in 1902 towards the tip of the peninsula, they explored rocks on James Ross Island. And this painter was able to actually find a number of fossils on the beach, including this steinkern of Hoploperia stokesi, as it became known. It was named after Frederick Stokes, the painter, which is essentially the shell or the carapace of a lobster. And alongside these specimens, he found bits of ammonites, snails, and bivalves. And Stokes was actually lucky. He left before the Antarctic winter set in on a resupply ship and made it back to the United States and donated his collection of fossils to the University of Chicago, where they were actually published on. Meanwhile, his Swedish colleagues who had planned to overwinter actually got stuck in the ice for 2 winters. And when they came back in 1905, after having been rescued by the Argentine Navy, were somewhat dismayed to find that these fossils had already been published by an invertebrate paleontologist at the University of Chicago. And to add insult to injury, he called their expedition a Belgian Antarctic expedition rather than a Swedish one. So these were actually the first fossils recovered from Antarctica that hinted at the fact that this place had once upon in its geological past been quite different than it is today. The representatives of invertebrates that had been found were unlike anything alive in Antarctic waters now. But these fossils, along with some fossil leaves from the Mesozoic that the Swedes recovered during their forced overwintering, were largely overlooked in much of the scientific literature. The most famous fossils, of course, were found about a decade later in the central Transantarctic Mountains here, which basically form the boundary to the polar plateau, the thickest ice being up here. And the central Transantarctic Mountains look like this in helicopter view. So you have the polar plateau stretching off the back of them, and then glaciers coming through this valley. And these glacial valleys have rocks that are Permian to early Mesozoic in age. And they also represent essentially the route by which early explorers tried to reach the polar plateau on the South Pole. Most notable among them, Robert Falcon Scott and his parties. Now, Robert Falcon Scott made 2 attempts at the pole. The first one was in 1904. And then subsequently in 1912, he actually did successfully reach the pole with his party of 5 men. He's seated here. And famously, of course, they lost that race to the pole to Norwegian Roald Amundsen, who better supplied with dogs and depots, was able to make the run much faster and much more safely than the British team. The British were partly hampered by weather and partly hampered by their own planning. Rather than using sled dogs, which they didn't have good experience with, they tried to man-haul their sledges. They originally started with a number of Siberian ponies, most of which died before they got through the central Transantarctic Mountains. And so they were essentially forced to haul their sleds. And that, of course, cost them a huge amount of time and energy. And on the return journey from the pole, they were starving. They were basically running out of food. And yet, despite that, this party of 5 decided to stop in the Permian rocks of the central transantarctic mountains to do some geology. And one of the things they found were these fossils of Glossopteris. The fossil they actually found is here on the left. The leaf impressions are quite faint. And here's a much better example of a leaf mat of Glossopteris fossils from elsewhere in the central transantarctic mountains, collected in more recent expeditions. But the fact that they found fossils of leaves, of essentially evidence of forests in Antarctica, they deemed so important that despite the fact that they were starving and they had they were jettisoning almost all the luggage from their sled, they hung on to these. And of course, famously, they died on the return journey, only 11 miles from a food depot they'd set up. And yet, the last thing that was found on their sled was 40 pounds of rock samples. That's how important they considered these fossils to be. But of course, despite this famous discovery and the fact that they had evidence of forests in a very different geological past, Antarctic exploration went into a major hiatus following Falcon Scott's death, and of course related to the two world wars and the intervening depression between them. So it wasn't until the 1950s that exploration of the interior, the geological history of Antarctica really began again. And it was prompted in large part by the sort of international community declaring the 1957-1958 International Geophysical Year would basically be a massive international effort to try and explore and understand the geology of Antarctica. And this was largely led by the United States. The United States Navy started the Operation Deep Freeze in the run-up to the 1957 International Geophysical Year. And as part of that, started founding a number of bases around the continent. These include three major bases that are permanent: McMurdo, Amundsen Scott, which is at the South Pole, and then Palmer Station at the near the tip of the peninsula. In addition to these three permanent stations, there were a number of temporary stations, including Little America, which was based out here. So this was a massive continent-wide effort supported by ships, aircraft, and helicopters of the Navy. And key to the exploration of the interior really was the founding of McMurdo Station here at the edge of the Ross Sea. And the reason that McMurdo was chosen here on Ross Island is that this is about as far south as you can get a ship through the pack ice. You can see one of the NSF's ships here. Off screen is an icebreaker that would have made a channel for these ships to get in. And it's no coincidence that this is the place they chose. In fact, if you look at the foreground of this photograph, here is Robert Falcon Scott's hut from Discovery Hut from his first expedition in 1904. This was as far as he was able to go. And he actually put in this hut, which was a prefab bush home he bought in Australia on his journey down. And you can actually walk into this place and still see frozen seal and penguin carcasses that his expedition and subsequent ones were actually feeding off of. Everything's frozen there. McMurdo today, of course, is a very different place. They are carbon neutral. You can see they're getting their energy from wind turbines up here. It's a major operation that can support up to 1,200 people. And it's essentially the gateway that allows for scientists to get into the interior of the continent. And it's allowed basically 50 or more years of exploration now, especially in the central Antarctic mountains. So expeditions would take off and be supported by aircraft and by snow machine and various tracked vehicles in the central transantarctic mountains. And you'd see these camps here, James Way camp huts from the 1978 camp and the 1985 camp at the base of the Cumulus Hills, which is one of the areas where fossils have been found. And the first vertebrate fossils in this region were found in 1969 by stratigrapher Barrett, who was basically measuring section here and came across vertebrate fossils. And in the following year, 1970, a expedition comprising geologists, including James Kitching, famous vertebrate paleontologist from South Africa, then started exploring the area and finding quite an abundance of fossils in the early Triassic rocks here. And with that, of course, started a new golden age, if you will, of Triassic or of Antarctic vertebrate paleontology. So these rocks you can see here are sedimentary, nice strata. They're interrupted by dikes and sills, so they're extensively volcanized by rifting that was related to Jurassic rifting of Gondwana. But the original deposits themselves, or the depositional systems here, formed as a series of foreland basins during the Permian and Triassic. And they were foreland basins sort of behind the bulge of the Panthalasan subduction zone, which lay slightly to the south in this region. And as they filled up during the Permian and Triassic times, then you started getting extensional rifting following those the late Triassic into the Jurassic that accounts for these volcanics you see up here. And of course, these are, again, Pangaean times. So we're talking about a very different system or a different geography to the world where all the continents are combined together. The Panthalasan subducting margin would be here along the southern edge of Gondwana. And then you have the forebulge behind it that's filling up with those sediments. And you have similar age sediments well exposed in in the Karoo of South Africa up here, as well as in parts of South America and the southern coast of Australia in Tasmania. And that's important to remember as we sort of switch our focus to the vertebrate paleontology and start talking about some of the fossils that occur here. Now, the lowermost unit, the oldest unit that's exposed in the central transantarctic mountains is the Buckley Formation. And this is a Permian unit, it's the Upper Permian. And unfortunately, thus far, it's devoid of vertebrate fossils. So we have no evidence of vertebrate or animals with backbones. But we do have a rich flora, mainly composed of different species of the seed fern Glossopteris, the very one that Robert Falcon Scott and his team found. So you have horizons with extensive rooting and even tree trunks, some of them erect, others fallen, as well as these large leaf mats that you've seen, and a number of fruiting bodies that actually tell us that the diversity of Glossopteris in this region was somewhat high. There are several different species that probably had different crown heights. So we have essentially a lush forested system with these seed ferns. They look quite modern in some aspects, but this is an entirely extinct group of plants. And then very suddenly, very dramatically, if you look at the rock record, there's a complete disappearance of vegetation. And that corresponds to the Permo-Triassic boundary, the largest, the most massive mass extinction in the rock record, where we believe somewhere between 75 and 90% of animal species and a very large number of plant species also went extinct. And so we go from this very abundant evidence of forests to essentially barren strata, mudstones without any signs of life. And then about a few tens of meters later, you start actually recovering fossils, which I will get to in a second. But this is where I want to take a turn towards a more personal part of it and talk about some of the fieldwork that I was part of in 2017 and 18 in the Freemouth Formation, the lower Freemouth Formation representing the lower Triassic in Antarctica. So our fieldwork took place in the Shackleton Glacier region, So very close to that camp I showed you before in the Cumulus Hills section of the Central Transantarctic Mountains. And this is what our camp looked like. So here, this smudge in the snow is actually an ice runway that was being serviced by ski-mounted aircraft, including LC-130s of the New York Air National Guard. And then we had a number of Jamesway huts, and these little dots out here, those are actually the huts that we stayed in. And I was a PI and a member of a broader team with team members from the University of Washington, the Los Angeles County Museum, Roger Smith, esteemed South African. And here we have Peter Braddock, who is actually married to Kathy Licht, who works with John Gudge, who you heard from a couple of weeks ago. So the Antarctic geoscience community is actually a pretty tight-knit and small group of people. Now, you can see the exposed rocks here above the glaciers running down to the Shackleton. And of course, these are about at 10,000 feet. Our camp was at 6,000 feet. The on-the-ground view of the lower Triassic sediments here shows a repeating sequence of lacustrine and braided stream deposits forming these cliffs, more sandstones that are separated by thick overbank mud deposits in these grayish green mudstones. And you have these cyclical sort of repeats of this going up and then getting somewhat sandier and a higher energy environment as you move into the middle Triassic. And as I mentioned, we're about 3,000 or 4,000 feet higher in section than our camp is. And we also have a long distance to travel. So all the work here is essentially helicopter supported. So we're dependent on being ferried in and out of our sites by helicopter. And that requires a fair amount of logistics, which is a lot of what the camps have to handle. Thankfully, for most of the last season, we had very good weather and lost only a single day to bad weather. On the ground, the fossil hunting isn't that different than it is many other places in the world. So you walk these exposures. Here you can see a volcanic dike or sill cutting through the sediments. And you're basically walking until you find fossils. This little smudge here is actually the skull roof of a Dicynodont. The rocks, as I mentioned, are intruded by volcanics, so they're fairly baked, which makes them quite hard. And so we have to use power tools in most cases. The silver lining is, of course, with hard rocks is that you don't need to rely as much on plastering and jacketing, which is much harder in this climate than in more temperate regions of the world. But the fossils can come out spectacular. So this is that Lystrosaurus. What you saw, the first thing that showed here was just this part of the skull roof. But the whole animal is there, beautifully articulated. And this is a juvenile specimen, about half the size of the biggest members that we get. So about 1.5 feet in full length. And it's probably the largest vertebrate that we get in this post-extinction early Triassic fauna. The most abundant thing we happen to find are amphibians. And this may seem a little bit counterintuitive because amphibians are, of course, thought of today as bellwethers for climate change and for extinction risk. But amphibians made it through the Permo-Triassic boundary in greater diversity than many other amniote groups. And we have a number of different groups represented, but they're very poorly known. Here's a skull of one. You can see the tooth margin. This is a different type, and we have at least 3 different families of these temnospondyle amphibians, these ancient relatives of modern frogs and salamanders represented there. So these are the most diverse animals to be there, and this is still largely a aquatically based ecosystem, which is not surprising because we still have no evidence of plants many tens of meters above that Permo-Triassic boundary. The Dicynodonts, I already mentioned Lystrosaurus. They are the largest and they are herbivores, so there must be some plants there, even though we're not finding too much evidence of them. We think that in life, they looked something like this. There are specimens of the same species from about the same age rocks in South Africa. that have scaly skin. And they have this turtle-like beak, but they also bear 2 tusks. And Dicynodonts are a group that have evolved in the Permian, survived the Permo-Triassic extinction. Animals like Lystrosaurus here are actually survivor taxa of that extinction event, and then rediversified later in the Triassic, making it to the late Triassic, but not into the Jurassic. And I should mention, Dicynodonts are actually synapsids, so they are on the lineage leading to mammals, even though they look reptilian. And some of their more mammal-like relatives that co-occur with them are the Dicynodonts, animals like Thrinaxodon, which you can see here has one of the hallmark features of mammals, which is heterodont dentition, so a differentiation of the teeth. And this is again an animal that is not just common in Antarctica, but is also found in South Africa. An artist's reconstruction, this is sort of a badger-sized animal, a small predator, and possibly may have had fur and had some ability to thermoregulate, which we can discuss later. Besides mammaline fossils, we also find fossils of reptiles, things like Procolophonids, a lizard-like but entirely extinct group of herbivorous reptiles. In fact, the first fossil we found in 2017-18 was this beautiful Procolophonid skeleton. Skull up here, forelimbs here, and the rib cage. Just split a rock and there it was. And one of the interesting things, and maybe one of the possible explanations for why these animals survived the Permo-Triassic extinction, is the common occurrence of burrows. So here we have a burrow structure. It's basically formed by sand, which infilled the burrow. The burrow was dug in this soft mudstone that you see here. A flooding event brought in this sheet of sand that then filled the burrow. And these are quite common. They're very similar throughout. They have a bean-shaped cross section. They descend at about 20 to 30 degrees from the top of the stratum. And unfortunately, they come in different sizes, I should mention. Unfortunately, we have yet to find a fossil inside one of these, but in South Africa, both Lystrosaurus, Thrinaxodon, and a variety of amphibians have been found in these burrows. So they seem to have been quite commonly used, and maybe one of the explanations for why these taxa survived the PT boundary, whereas others didn't. And so I've mentioned a number of times now that the species we find in the early Triassic of Antarctica and the Lower Fremont Formation are shared with South Africa, so much so that it's not just the same genus, but it's actually the same species in many cases. And when this first was discovered in the early 1970s with those first expeditions, it was actually a landmark moment in geological history. So the idea of continental drift, which of course I grew up with and which seemed very obvious and logical to me, was by no means a accepted fact in the 1950s and 60s. But with ongoing research on mid-oceanic ridges and elsewhere, it was becoming slowly a overwhelmingly well-supported hypothesis. And one of the lines of evidence for it dating back to Wegener was, of course, the distribution of fossils. And so when the same fossils were found in Antarctica that as in Southern Africa, this was heralded as one of the strongest lines of evidence yet adduced in support of Gondwana land and correlatively of continental drift. So the discovery of these Antarctic fossils actually played an outsized role, one can say, in establishing continental drift as a mechanism for geological change. And we now know that besides Antarctica and South Africa, a number of these animals, such as Lystrosaurus, now occur on other continents, including India. And the same is true, in fact, of the Permian Glossopteris, which is distributed on almost all Gondwanan continents. So taken together, these fossil distributions indicate very strongly that the continents were together in the distant past, and that they essentially shared represented an unbroken biogeographic region or biogeographic province at that time. Now, as we move up in time, we move from the lower Freemouth Formation towards the middle Freemouth Formation. We see a change in the fauna. Some of the fossils of which we have, and they're generally more fragmentary, unfortunately, in these upper layers, have been likened to the Cynognathus fauna, again, of South Africa, or the Cynognathus assemblage zone. So those similarities still exist. But with respect to some of the things that have been found from the Middle Triassic Freemouth Formation, especially in the Gordon Valley region, we start seeing unique animals that don't have representatives or conspecifics in South Africa, but are unique to the Antarctic. And these include a couple of giant amphibian species, including Antarctosuchus here on the left and Cryostega on the right. So when I say giant amphibians, I'm talking about alligator-sized animals. The skull of Antarctosuchus here is about 60 centimeters long, so about 2 feet long. Cryostega, we only have the tip of the snout, so this actually corresponds to about that amount of the skull of Antarctosuchus, but it's about the same size. So these are temnospondyle amphibians. We can actually see some ecological diversity in the fact that Cryostega has these massive tusk-like teeth that you see here, as well as on the palate, whereas the dentition in Antarctosuchus would have consisted of hundreds of tiny little teeth along the margin of the jaws. So this animal is probably a fish-eating specialist, whereas Cryostega more fulfilled the ecological role of an alligator, taking larger prey, including probably terrestrial animals that ventured too far into the water. Importantly, these are unique species to the Antarctic. They have relatives on other continents, but they are different, at least at the species and probably at the genus level. So we're starting to see some differentiation of faunas in the Antarctic. And the most recent piece of evidence for that is something we published just earlier this year. This is the back of the skull of a very large Dicynodont, so a relative of Lystrosaurus, called a Kannemeyeriform. And this is basically where the skull would attach to the vertebral column, and this keyhole-shaped thing is where the spinal cord would come out of the brain case. It's not much to go on, but there are some unique features that make this large Dicynodont somewhat different from ones elsewhere in the world. We didn't feel strongly that we had enough evidence to give it a new species name, but we could also not refer it to a species from any other part of the world, again, suggesting that you have a somewhat distinct fauna in Antarctica during the Middle Triassic. And just to give you an idea of size, this Triassic Kannemeyeriform would have been around the size of a hippo. So these are quite large animals. And this goes hand in hand with the fact that we are starting to see the ecosystem change. So we start having the evidence of peat and coals. This is telling us that we actually have vegetation coming back in significant amounts in the Middle Triassic. And this is a trend that, of course, continues into the Upper Triassic. So the Upper Triassic, much like the Upper Permian, unfortunately, shows a lack of vertebrate fossils, but an abundance of plant fossils that include a number of fossil ferns like Dicroidium, that you see these nice leaves here. Two different leaf morphotypes, but they would have been on the same tree. And these are not the ferns you see in your backyard growing in disturbed soils. These are tree ferns, more like the ones you see in Australia and New Zealand. We see very large horsetails. Neocalamites would have the same anatomy as a horsetail you might see at a pond in a park near your house, except these things would have been 10 to 20 feet tall. And in a number of sites, you actually get tree stumps in place. So this is, you can see the roots coming off this stump. This is actually a stump in situ, standing erect. In some places you even find fossil forests in the Upper Triassic of conifer-like trees. Now, these are high latitude forests. They would have been at a latitude where no trees grow today. Again, a clear indicator of much warmer climates. And they also show very unusual patterns of growth in their tree rings, unlike anything we see today, because they are at such high latitude. And then we see a shift in the kind of preservation, and this is partly because we go from filling a foreland basinal system in the Triassic to more of an extensional rifting system in the lower and middle Jurassic. So basically, as the continents, as Pangaea is starting to rift apart, those rifts are displacing into the central transantarctic mountains, and the rise of the central transantarctics themselves. This is a rift mountain chain. So we see that process happening there. But nevertheless, that still gives us a nice basinal system for deposition. And so it's in the lower Jurassic that we find perhaps the most exciting, at least to myself, fossils from the Antarctic, which are, we have a dinosaur fauna in one of the earliest Jurassic dinosaur faunas in the world, and a remarkable one for its richness. And as with so many other dinosaur discoveries, this one was partly due to luck. So the first find of bones was in 1990. This was basically a femur of a dinosaur discovered by geologist David Elliott from the Ohio State University, who wanted to approach the volcanics that are exposed at the very top of the central Antarctic mountains that basically cap the series of depositional rocks there. And on the way, he came across this giant bone that's about 70 centimeters long. And as luck would have it, he was based at a camp where Bill Hammer, long-standing paleontologist with an interest in Antarctica, was working, actually collecting those Triassic amphibians I showed a few slides ago. And so Hammer broke off his work and went up to Mount Kirkpatrick to look at this bone, and immediately realized, based on, if nothing else, its size, that he had a dinosaur on his hands, and started excavating that in 1990 and 91. This was then followed up by a second expedition in 2003 that collected some more of the dinosaurs that were on Mount Kirkpatrick. And then finally in 2010-11, I joined Bill here along with Phil Curry from the Royal Tyrrell Museum, or the University of Alberta, and some of our other crew, including my then graduate student, Nate Smith, you see over here, now at the Los Angeles County Museum, to really finish up this quarry. And so we spent 6 weeks basically excavating something like 20 tons of rock using power tools. We were based, the site is at 12,500 feet, so we couldn't camp up there. We were based at the Central Transantarctic Mountain Camp, about 25 miles away, at much more pleasant altitude of 6,000 feet. This was a joint US-New Zealand camp, and you can see we had nice support and infrastructure here, very similar to where we were in 2018. And again, this is sort of our living quarters during that time, with nice Permian and Triassic exposures behind us. Now, as I mentioned, the site itself is one of the highest peaks in the Central Transantarctic Mountains. So at 14,000 feet, we have the volcanics capping Mount Kirkpatrick. And then off the shoulder here, in these more buff-colored sediments, we have the early Jurassic rocks of the Henson Formation. And from this one little area, perhaps not much bigger than a football field, we actually have 6 dinosaur skeletons. So the main Cryolophosaurus quarry, the main quarry that was found in 1990, is here. It's yielded actually parts now of 3 dinosaurs, including 2 meat eaters, and parts of a plant eater. And then we found subsequently 2 more plant-eating dinosaur skeletons, herbivorous dinosaurs nearby. And then in 2003, the expedition found parts of a 4th one just off the screen here. And so this is really the only place in the central transantarctics where dinosaurs are found. We have followed these layers laterally on other mountain tops without any luck. But right here, this is the bonanza, 6 skeletons in the area of a football field, or not much more than that. And as with the Triassic rocks, everything here is silicified and baked. It needs to be worked with power tools. Obviously, we're dealing with very large animals. Everything has to come out in blocks and then be carried down to a helicopter landing spot or placed in a cargo net that can be hooked below the helicopter. So the largest piece we took out of here weighed about 600 pounds. Most of our other blocks were around 100 to 200 pounds. But in the process of the 2010-11 season, we ended up collecting about 5,000 pounds of rock. And we had to move another 20,000 to get to those 5,000. So this was a significant amount of work under very difficult conditions. And the dinosaurs we get are unique. So the most famous one is, of course, the one found in 1990. This is Cryolophosaurus. It's a carnivorous dinosaur named for this unique crest on its head. The name means frozen crested lizard. And we have the back end of the skull. This is the real fossil with a couple of vertebrae stuck to it. This is a reconstruction of the front of it based on other close relatives, such as Dilophosaurus. And at around 25 feet and weighing about 1,000 pounds, this is actually one of the earliest large dinosaur predators of the Jurassic era. So we have dinosaurs, of course, in the late Triassic, but there they are smaller and living alongside other bigger predators belonging to the crocodile line of archosaurs. After the Triassic-Jurassic extinction event, dinosaurs take over, become the top predators, and Cryolophosaurus is one of the largest among them. This is a full-size skeleton where we now have part of a skull, most of the vertebral series, and shoulder girdles, hind limbs, and a good section of tail. The only parts that are missing and that have been filled in from closely related animals are actually the tip of the snout and then the hands and feet. So this is a very well-known dinosaur. And we actually have 2 specimens from the same quarry, one slightly larger than the other. And as I already mentioned, Cryolophosaurus is sort of belongs to this group of early Jurassic dinosaurs. So they're sort of in between the Triassic coelophysoids and not as derived or advanced as some of the dinosaurs you're more familiar with, like the Coelurosaurus, to which T-Rex and birds belonged, or Allosaurus or Spinosaurus. So sort of an early radiation in the Jurassic of these mostly crested mid-sized theropods. They're not exclusive to Antarctica. We have, of course, Cryolophosaurus in Antarctica, but its relatives include Sinosaurus from China, also with crests on its head, and Dilophosaurus from North America. So again, this is a radiation that seems to have arisen very quickly after the Triassic-Jurassic boundary and spread out across the globe with similar but slightly different looking species on all continents. And we know a lot about Cryolophosaurus. We've actually done histology on it. This is where we section the bones to infer how old an individual specimen might be by counting up growth lines, and also estimating how fast it grew. So this is a rib of Cryolophosaurus. Based here, we can see actually 9 different growth lines. And by back calculating missing ones, we estimate this animal would have been around 15 or 16 years old and would have reached adult size in approximately that amount of time. So a fairly large but somewhat slow growing dinosaur. We also know something about the brain shape based on CT scanning, where we can see that in many features, this theropod dinosaur lies in between a typical reptilian brain anatomy and what we see, for example, in birds, which are descendants of theropod dinosaurs. So we note that the front of the brain and the back of the brain are angled relative to each other. This is the forebrain, there's the hindbrain and the midbrain. And that angling is something we see in birds. In a typical reptile, a lizard, or a crocodile, you would have a much more linearly arranged brain. One of the unique features we see is this pneumatization. These are air spaces that would have occupied the brain case. And this is a typical feature of many archosaurs. So we're learning a lot about the paleobiology of this unique dinosaur. In the same quarry as Cryolophosaurus, we have found remnants of a herbivorous dinosaur, apologies for that, which we've named Glacialosaurus. Glacialosaurus is a sauropodomorph, so it's a relative of the long-necked, large sauropods like Brachiosaurus, Brontosaurus, Apatosaurus that you're all familiar with. A slightly smaller version of that, weighing around a ton, and being about, again, 25 to 30 feet long. And we don't have nearly as much of this specimen, unfortunately, as we do of Cryolophosaurus. We have parts of the foot and the hind limbs, but there's enough there to actually tell us it's different from other known sauropodomorphs from this time period. And so we can fairly confidently diagnose this as a new taxon. So we have a predator and we have a potential prey species forming, the beginnings of an ecosystem. But our luck or our fortune didn't end there. So in that 2010-11 season, as I mentioned already, we found two more sauropodomorph dinosaurs very close to each other. The remains of one are here, and the remains of the other are right over here, right under this overhang of rock. And starting with the more complete one, which is actually based on two skeletons that were collected here, we have a beautiful skull of this species, which we have nicknamed Jolly Roger in honor of Roger Smith, who found the specimen, and a true scientific name will be forthcoming. But besides the skull, we have these two skeletons. You can see forelimbs marked here in orange based on CT scans, shoulder girdle elements in red, and vertebrae in yellow. So two partially articulated skeletons that give us a very full understanding of this anatomy. And this is a very small animal. If we actually, just for a sense of size, here's that model from an exhibit we made alongside my two children who were 9 and 6 at the time. So this is a very small dinosaur. And one of the questions we were, of course, curious to know is this simply a small species, or are we dealing with juveniles? And in order to answer that, we used the same histological techniques I showed you for Cryolophosaurus. And we cut a variety of bones. So the leg bones seem to indicate very, very rapid growth and no growth marks. None of those lines of arrested growth that you saw in Cryolophosaurus, suggesting that this animal is extremely young. Now, if we look at some of the other elements like the ribs, we do see growth lines in parts of them, suggesting that perhaps they're not quite that young. They may be 1 or 2 years old, but still growing fast, still immature, and still juvenile. So the reason these animals are small is that they are in fact juveniles. The differences in the leg bones suggest they would not grow into Glacialosaurus. They represent something different, but we don't actually know how big they might get. And very nearby, as I mentioned, we found parts of yet another skeleton. This one is a little bit bigger, but not by much. There's Glacialosaurus for comparison. But again, sufficiently different that we think we have a new species. Likely not fully grown, but more mature than our Jolly Roger specimen. So with these 3 different species from Antarctica, we can then again ask this question. Okay, so they're endemic in the sense that they don't occur on other continents, but where do their nearest relatives occur? And what does that tell us about the separation of the Antarctic continent from the rest of the world at this time? And so we can look at this in terms of biogeography. We can look at what are the closest, what is the distribution of the closest relatives of our Antarctic species? In each case, whether it's Glacialosaurus, Jolly Roger, or the third specimen I just showed you, their nearest relatives actually occur on different continents. So the three Antarctic species are not each other's closest relatives. They are endemic species, but they do not belong to an endemic radiation in Antarctica. Rather, their closest relatives occur all over the world. So again, the separation of Antarctica at this time from the rest of Pangaea and from the rest of the world was incomplete. Animals were able to distribute as they speciated and evolved. They distributed fairly freely across the globe. So we still don't have, the sort of patterns of separation where we see, for example, animals in South America or in Australia forming unique groups that are found almost nowhere in the world today. So we can actually use the distribution and the evolutionary understanding of our fossils to really tell something about the geologic history of the place at the time. And I'm going to wrap up quite quickly here and open up for questions. But before I do, I just want to make a plug for a exhibit that actually showcases some of these dinosaurs. Here's a beautiful life-size model of Cryolophosaurus with a mural. This exhibit is traveling. It was created by the Field Museum in partnership with several other museums. It's currently at the Utah Museum of Natural History. So if anyone's going to Snowbird or Park City in the coming months for a spot of skiing, you might want to stop in and see this. And after that, it'll travel to Buffalo and several other venues, hopefully even the Science Museum here, if they might be interested in taking it. So I encourage you to see it. It's a 7,500 square foot exhibit. And besides these beautiful models, we actually have the original fossils of Cryolophosaurus, Glacialosaurus, and all the other specimens you've seen in this talk in the exhibit. So I encourage you, if you have a chance, to see that. And with that, just to summarize, Antarctica's Mesozoic fossil record is obviously meager because it's a hard place to get to, and so little of it is exposed above the ice. But what we do know is that we have an ice-free past that supported, where the continent supported ecosystems with plants and animals, hinting not just at connections to other land masses, but also to unique evolution within the Antarctic continent itself. Unfortunately, there are no animals in the Permian record, but we do have those rich Glossopteris forests connecting Antarctica to the rest of Gondwana to the southern continents. And then as we move up through the Triassic, we see great similarities to faunas elsewhere, in particular South Africa, and that's slowly changing with an increasing degree of endemism in the fossils we find in Antarctica, culminating in the Jurassic dinosaurs that are unique in many ways and not found elsewhere in the world. And with that, I'd like to acknowledge the National Science Foundation, without whom this work wouldn't have been possible, both the field work and the subsequent research. And of course, the many people who have participated in the field work, in the science, both students, technicians, and my co-PIs on the various grants. So thank you for taking time to listen to me, and I'll open the floor to questions now.
Well, thank you, Peter. That was wonderful. Really enjoyed it. We do have some questions, and I will, the first question came on fairly early from Mark, and I'm going to add to it before I let you answer it. The guy with the hammer has no gloves on. It doesn't look like delicate work, so why no gloves? And then I'm going to add to that and just ask, in what kind of typical temperature and wind conditions did you work? I mean, the pictures make it look pretty nice, but I don't know.
Yeah, that's a great question. So, James Kitching here is not wearing gloves. This site is actually called Thrinaxodon Col, because Kitching here found 6 or 7 Thrinaxodon skeletons on that avulsion surface he's on. So you see that kind of reddish pockmarked surface that he's resting on it's actually an avulsion surface where you had a flooding event. And there were 6 or 7 skeletons in there of this rather common cynodont, Thrinaxodon. And so he didn't have power tools at the time. So he's actually trying to take these out by hand. He did quite well. You can see the holes there and even the plaster that he applied still to this day. Erosion's very slow, obviously. So one of the things that, working with gloves is it's really hard, for example, to hold your chisel or awl the way he is. And not having power tools, they would have obviously had to, use their bare hands. Sometimes, yeah, if you're doing delicate work, you have to take your gloves off. It's not pleasant. You don't do it for long. But here at in the Cumulus Hills, you're about 9,000 feet on a mild day with great sunshine and not too much wind. It'll be 15 degrees. So it's not bad. Folks in Minnesota wouldn't complain about 15 degrees, I think. Now, if you get up to Kirkpatrick, where the Jurassic dinosaurs are from, the temperatures are usually around minus 20 Celsius all the time. And so you really don't want to take too many layers off. But that's much harder work because you have to jackhammer. So you're sort of continuously taking your jacket off, putting it back on, taking it off, taking it out, one thing I found out is if you take your gloves off, as I did once when I was trying to take one of those helicopter videos, helicopter taking off, and you got an exposed hand on your video camera and the rotor wash comes in, your hand freezes very fast. I thought I'd gotten frostbite, but thankfully I didn't.
So I take it there are some days when you can't work because it's either too windy or too cold.
Wind isn't the big problem. The big problem is because we're landing in helicopters. You need visibility. There's the issue is being able to land. So in 2017-18, when we were at Cumulus Hills, we had great weather. All these photos you can see are quite wonderful. Wind can be a problem when you get close to the polar plateau. You get katabatic winds, basically the dense cold air flowing off the plateau. And so you'll have, 40, 50 knots, 60 knots sometimes coming off. But the pilots are pretty good at working with that. The biggest single problem is visibility. And so in 2010-11, when we worked on Kirkpatrick, we lost a fair number of days to visibility. So the entire camp and all the crews are supported by 2 helicopters. This is one, and 36 Julie, 36J is the other one. And so basically they'd walk out and they'd look over, you could see Kirkpatrick, and if it was clouded in, they would call off your flights and reassign them to other teams, and then clouds might clear later in the day, but you were already stuck. So for us, the biggest problem was always visibility. And even if weather was reasonably clear, you have to remember they can only make one pass coming in, because even if with a little humidity in the air, if they have to have multiple passes, the contrail from the jets on the helicopter will actually cloud up the landing site.
Thank you. Question from Dave. First of all, he says, excellent presentation. What tempted you to study paleo?
Oh, I was one of those kids who never grew up. I have my first dinosaur book that I got when I was 3 years old. It has the old Rudolf Zallinger pictures in it. The guy who did the big murals at Yale. And I just never lost the interest with it. And then, when I went to college and got the opportunity to study it, I just stuck with it. So that was my, you know, I was one of those kids who never grew up. That's essentially the story.
Okay, a question from Paul. When did Gondwana land exist?
Okay, so Gondwana, let me go back to, do I have a map of Pangaea? Yeah, here. So Gondwana is basically refers to the southern half of Pangaea. So the continents of South America, Africa, India, Australia, and Antarctica. And we think that the Pangaean, the Pangaean sort of reconnection or the formation of Pangaea through accretion was completed somewhere around 350 or 300 or 380 million years ago. And then you have Pangaea basically lasting until the beginning of the Jurassic. So roughly around 205 million years ago, you start getting a rifting between Laurasia, so the northern continents, and then Gondwana, which are the southern continents. And then the southern continents continue to be connected until the Cretaceous, and then you start seeing splitting. And there's some disagreement whether it's sort of the opening of the Atlantic between South America and Africa first, or you have rifting occurring on the east coast of Africa between India, Australia, and Antarctica. But that rifting, as I mentioned, is initiated sometime in the early Jurassic and then propagates, and it's essentially responsible for the volcanics that you see at this Kirkpatrick basalt in the middle Jurassic is actually related to that rifting, and is also found, its equivalents are found in the Drakensberg in South Africa and in Australia. I forget the name of the unit there. So you basically have this rifting initiating in the middle of the Jurassic, and then up through the Cretaceous, you start then splitting off the Gondwanan continent. So Gondwana as a unit is together from from before the Permian and in up to basically the beginning of the Cretaceous. As I mentioned, there's some disagreement which order, what split off first. Was it South America or was it Australia? But by 80 million, these are largely isolated.
Okay, thank you. A question from Mike. You mentioned heterodont dentation in a creature. Was this a therapsid, and are there therapsid fossils in Antarctica? You probably know what I'm talking about.
Yes. Therapsids include Thrinaxodon. It's one of the earlier therapsids, and I'm trying to find it. I'm going the wrong way. No, I'm going the right way. You have obviously Thrinaxodon. Sorry, I should apologize. Thrinaxodon is a cynodont therapsid, so a little more advanced on the mammal line than Lystrosaurus that you saw. And you have actually more derived therapsids in the middle Freemow, or in the middle Triassic upper Freemow, including some unpublished material that we have from this latest expedition. And so these are things that are even more mammal-like or closer to mammals in terms of their evolutionary relatedness than Thrinaxodon. So an even larger degree of heterodonty, a clearer distinction between the canines and the chewing cheek teeth, and a bigger reduction of the bones at the back of the jaw. So in mammals, we have one jawbone, that's this one that carries the teeth, and the other bones that ancestrally would have been in the jaw actually have migrated into our ear. They form our inner ear bones and the ectotympanic around the ear. So one of the new fossils we have shows a progression of that, and it's more mammal-like than even Thrinaxodon. It's not been published yet, but it's one of the finds from this last expedition.
Okay. I have a question for Paul. He's referring to, I think, your earlier answer. He just asked, is that 15 degrees Fahrenheit? I think you were.
Yes. A nice day at Shackleton would be, at high noon would be around 15 degrees Fahrenheit. So, good Minnesota weather.
Yeah. Question from Faye. Did you find any geological time gaps?
Well, we have gaps in the fossil record, and we have only, so if we look at the geological column, we have obviously some radiometric dates that have been collected, particularly for the upper part of the sequence, and a number of dates that have tried to pin down the Permo-Triassic boundary. But we're really talking about relatively few radiometric dates. So we're not entirely sure how much might be missing in terms of the, parts of the Triassic in here. Now, when we go to the upper Freeman Formation, and also the middle Triassic Freeman Formation, we get some higher energy depositional environments where we have a lot of channel sands and scours. So it certainly suggests that we have a number of unconformities in there. So there are probably some missing bits up there. And then we don't have a clear Triassic-Jurassic boundary either. So you can see these disconformities that are marked here. So those are places where we really don't have good information. We haven't been able to peg down the Triassic-Jurassic boundary, which usually is pretty easy to find globally based on paleontomorphs. And there has been some paleontomorph sampling done. So that's one of the places we find a fairly obvious one. And then again, these higher energy Freeman formation units, there's an unconformity or disconformity in there too.
Okay, and I think you have the right slide up for Angie's question. Tell us more about the Permian Triassic extinction. What caused it?
So there's been a lot of debate about the Permo-Triassic extinction event. It's a fairly short-lived event. So it's certainly on the order of 60,000 years or less, with dating based on marine sections, mainly out of China, where you have a good boundary section. And radiometric dating has been done there. What we know definitively happened, and we know this from carbon isotope sampling, is that you have a massive increase in CO2 at the boundary, and that matches up very well with the dated section. So your carbon isotope stratigraphy shows a massive negative excursion in carbon. And if you look globally, that seems to coincide very well with not just the disappearance of plants and animals, but a change in erosion. And you go from kind of more in a lot of places, especially in South Africa, but also in Siberia and elsewhere, you go from, sort of mudstone, lacustrine environments to highly oxidized reddish sediments with braided streams. So it tells you you're changing the environment. You're basically going from kind of swampy lowland environments to dry environments devoid of vegetation where water runs off and runs off fast. So it's forming these braided stream environments because there's no vegetation to catch it. I should mention that those scenarios have been challenged at individual sites, whether there really is a global signal or you might have a tectonic signal some places where uplift is actually causing that braided stream type deposition. But it is very telling that, you get those braided stream deposits mainly identified in places like South Africa and Siberia, but you actually see the same thing. I'm looking for the right slide. Yeah, here in Antarctica. So you get this, these massive ledges that are on the order of 2 to 3 meters high. And if you look at them, they're quite scoured. They have that traditional braided stream depositional environment that seems to, again, coincide with or be well explained by a lack of vegetation and rooting horizons that could actually capture water and slow down the runoff so you don't get that alluvial braided stream type deposition. Now, what causes the CO2 spike in the atmosphere and the heating and drying of the environments? There's the immediate culprit that I think everyone agrees on is that you have these massive lava flows in Siberia. So you have these traps. Many of you have probably heard of the Deccan traps of India that coincide and bracket the Cretaceous Paleogene extinction. But the Siberian traps are far more massive. So we're talking somewhere on the order of like a million cubic, million cubic kilometers of lava over a very short period of time being emitted. And of course, the associated degassing of CO2 and sulfur dioxide and other greenhouse gases would be responsible for it. And there's some debate whether that alone was sufficient. Some people have come up with models of these lavas actually puncturing through coal-rich Carboniferous Mississippian deposits and burning off that coal to add to it to make sure you had, to make the spike big enough to get the effect you see on the climate. But in one way or another, those Siberian traps and the associated degassing of CO2 and sulfur dioxide, which is a much more potent greenhouse gas than CO2 even, are responsible.
Okay, I have a double question here from Patrick. The lack of plants amid plant eaters had me wondering if there might be a reason, perhaps volcanism, that plant fossils might be missing.
Yeah, so there's a number of reasons why plants might be missing. One is obviously the right depositional environment, and it's not uncommon that when you find good plant fossils, you don't find good vertebrates, and vice versa. So that's not sort of the telling thing, but the more telling thing, I think, in this case is the fact that you go down here into the Permian and you have not just plant fossils, you have entire forests. You can, this is Kitching Ridge. It's not over here, but you go 10 miles to the east, and it's very hard to orient yourself when you're right next to the South Pole. And you get to Collinson Ridge, and there's a fossil forest. There's just trunks coming out of the rock. There is stumps. There's leaves. There's every kind of plant organ preserved. And then you move up section, and you literally find nothing. And you move up section for hundreds of meters before you start finding coals. And when you find coals are basically evidence of an overabundance of plants. So the plants are not being consumed or decaying fast enough, and therefore becoming part of the fossil record again. And so you have this very long stretch of time representing essentially most of the, if not all of the early Triassic, so some tens of millions of years, where you're not seeing plants. Now we know plants must have been there because obviously Lystrosaurus here is a plant eater. So there must have been enough vegetation around to support this animal. But this is a relatively small animal. I mean, this is a dog size. The biggest Lystrosaurus specimens are probably the size of a sheep. And every other herbivore is smaller. So you don't have rich vegetation that can support the much larger animals, such as the hippo-sized Kannemeyeriform that I talk about for the Middle Triassic. And it's really the reappearance of these coals in the middle Freemouth Formation that are telling us that vegetation has come back in some substantial quantity. So that's really sort of the marker we're looking for. And this isn't just here. This is the same elsewhere in the world where you have a good record, be it South Africa or Siberia.
Okay, the other part to Patrick's question is, he's wondering if the type of animal might hint as to what sort of flora supported them.
That's a very good question. So we know from other parts of the world, including Europe, that the lower Triassic is dominated by a plant called Pleuramia. And that seems to be sort of a common plant type. We don't know how globally distributed, but it certainly is fairly widespread. We don't have, as I said, too many other plants. And again, these Pleuramias are, they're not huge plants, they're not trees, they're more sort of sedge-like things with a short, 6-7 foot trunk. And again, a fully extinct plant group. So we don't actually have an abundance of plant fossils. And we don't have, of course, good modern analogs for what would eat them. So if we look at the most abundant herbivores we have, which are these Dicynodonts in the early Triassic, they have a turtle-like beak and these two tusks that in some species appear to vary between males and females. So there's some sexual dimorphism there in at least some species. So we can't really tell much more than that they probably were, they most clearly were herbivorous. They have a very weird lower jaw anatomy that would have allowed them to kind of do a chewing back and forth motion, rocking motion of the lower jaw. But what that might be well suited for, it's hard to say. The closest modern analog we'd have is some kind of turtle, but that's, it's not very telling.
Okay, a question from Carol. She says about slide 50, hindquarters are shown with what looks like desiccated flesh. Is it?
Slide 50, let me.
Well, approximately.
Switch screens. Sort of here. That's my 40, that's my 50.
I will, just a second. I think I'll put if I can get Carol going here, she can talk. Carol, I think you have to unmute yourself, but then you can talk.
Okay, I'm here.
Yeah.
Well, go up or down. It's somewhere in this vicinity.
Oh, are you talking about
There you
this?
go. That's the one.
Oh, yes. This was actually a good point. No, this is from the exhibit. And so what we did is we basically created a bas-relief model of the dinosaur, and then we 3D printed copies of the bones we have. So you get an idea of, this is the parts we actually have. We have the ankle and the foot bones and part of the knee. And this is what we think based on relatives, what the animal looked like. So the other part of that is here. So we have a bas-relief of the two different species, Glacialosaurus being the bigger one. So rather than sort of well, in a sense, they are defleshed in the sense that we're trying to show, here's the material we have, here's what we think the rest of the animal looked like. So in life size.
Thank you.
Okay, I'm going to unmute phone number 8631, see if you have any questions.
Hi, it's Mary Helen. Can you hear me?
Yeah,
I
it's kind of
can.
a buzz, but we can hear you.
Okay. My question is, you mentioned that currently extant, the only land species pretty much is arthropods. I'm curious, are you finding fossil arthropods, and what arthropods are now still alive there?
Yeah, so we have not found fossil arthropods, and I think that's largely a function of the types of rock we are looking in. The best evidence we do have that there were arthropods of various types are from some of those Glossopteris leaf mats that I showed you actually have herbivorous predation. So we know that insects actually ate those leaves. So we have trace fossils, if you will, of arthropods from those Glossopteris leaves. And again, in the upper Triassic, you do find leaves of various types with feeding marks from insects on them. So we know definitely without a doubt that there were insects and various other arthropods in the Mesozoic and the Paleozoic of Antarctica. In the present day, the things that are found are springtails. So there was some springtail. Actually, when we were at Shackleton camp, there was a group of biologists trying to look at these very simple three-component, ecosystems that are like moss, springtail, and daddy long legs that ate the springtails. And they actually found some springtail that had only been found once before in 1962 or something. So it was very remarkable. It was microscopic little white thing. So that's essentially what there is. The most extensive place you find these are, of course, in dry valleys region near McMurdo, where you have an ice-free area, and you have some lichens and mosses, and you have these simple systems. And then, of course, as you go to more temperate parts of the continent, particularly out towards the peninsula here, you start getting a more diverse flora of including grasses and sedges of various types, and presumably those support a greater diversity of arthropods that I don't know enough that I can speak to that though. And the only other place I would imagine that you find some kind of arthropods are things like feather lice on the birds. So besides the penguins, you also have things like skuas and a few other seabirds that might support feather lice and other arthropod, other insect parasites, ectoparasites.
Okay, thank you.
Okay, I got a couple of questions here. I've got all the audience questions, I think. You mentioned growth lines on some of the fossils. Do we know those are annual?
So yes, we can infer that they are annual because we can look at living animals, living reptiles, and even mammals, and actually find the same types of lines of arrested growth, as we call them, or other markers in the bones. So in a lot of dinosaurs, and especially in theropod dinosaurs, you get very clear lines of arrested growth. Sometimes you get a double lag, like this is actually a double. We would count that as 1 year, even though it's doubled up. Other times they're fainter. You might get what you call an annulus, so it's not a distinct line where growth stopped. And what these essentially, if you look at the pattern of them, what they basically mean is that growth stops and you don't get this porous structure where you have these individual channels for blood vessels that are, the bone grows by blood vessels going through and depositing essentially new bone material around them. So when you get these lines, it means that that process has stopped. And if you look at living reptiles, alligators, turtles, lizards, but even some birds like moas that were fairly slow growing, these seem to coincide pretty well with either the winter in more temperate regions or with the dry season in more tropical regions. And they will form even in lab animals. So even if you keep animals under constant light and temperature conditions, this does happen. So it is sort of an annual circadian type pattern. It's not something that's just mediated by patterns of light and darkness or seasonality. It's not an ecological response in that sense. Which otherwise would be very interesting, because one of the reasons we're doing this in Antarctic animals is that even though it was clearly warmer then than it is today, these animals would still have been subjected to winter darkness, long winter darkness, and presumably lower productivity from plants. So you might expect them to grow slower or differently from their relatives on other continents. And it turns out they don't actually. Cryolophosaurus here grows pretty much like theropods elsewhere in the world from the early Jurassic and even from the Cretaceous. And the same is true of our little sauropod A here, Jolly Roger. It's a small animal, but at this size, it's actually already bigger at a younger age than Musaurus, which is another sauropodomorph of early Jurassic age from Argentina, so from a more temperate part of the world. So there doesn't seem to be any sort of, the fact that they lived in winter darkness at high latitude does not seem to have affected their ability to grow at the same rate as other dinosaurs from more temperate regions. One interesting thing, which I didn't mention, but when we get back to Lystrosaurus here, is that recently a couple of my colleagues who were part of the 2017-18 expedition cut the tusks of these and found sort of growth patterns. I should mention these tusks are ever growing. They don't actually get replaced in Lystrosaurus. And some of the growth marks they see in the tusks there look more or less like hibernation marks that you see in the teeth of some animals today. So it's a possible indication that at least Lystrosaurus in this part of its range in Antarctica might have been a hibernating animal, and likely hibernated in one of those burrows that we find there, a bigger version of this.
Okay, I have one more question. Early on, you mentioned amphibians that could possibly have some thermal regulation. Could you talk a little more about that?
Did I? That's not what I meant to say. So if I did, then
Maybe I
apologize.
misunderstood.
I confused myself. No, I think the way to look at the amphibians is we obviously know that amphibians are cold-blooded. And so if you have very large amphibians, the size of crocodiles, like we do in the Middle Triassic, they're going to be an indicator of much more favorable climatic conditions than you have today. I think one thing I also mentioned about amphibians is that they have a very high diversity in the early Triassic. And this is sort of an indication that even though we think of amphibians as being very environmentally sensitive animals today, with lots of potential things affecting their biology, including, sort of estrogen-like substances being released in nature that are interrupting breeding patterns, to acidification of waterways. But in contrast to this idea that amphibians are very environmentally sensitive, they seem to be one of the groups least affected by the Permo-Triassic extinction event. So they are the most diverse species-wise and the most abundant fossils we find after the PT boundary, which is perhaps not what one might expect, but
Okay, thank you, Peter. I don't see any more questions. I don't have any more questions. So I'm going to thank you for a great talk with great visuals. I enjoyed it very much, and I got a number of comments saying that our audience enjoyed it very much too. So thank you.
thank you so much, and it was a great pleasure to talk to you guys. I hope I get an opportunity to do it in person sometime in the near future.
I'm sure Steve is listening and taking note of that.
Okay. All right,
Okay, well,
everyone.
good night, everyone.
Have a good night, and thanks again for inviting me.